Okay, welcome everyone to the Slightly Autumn seminar. And very happy to have as our speaker today, Elliot Kinsel of the University of Maryland. So Elliot is a fourth year undergraduate student in mathematics and physics, I guess mostly mathematics at Maryland. But he's been working remotely with me. So he's been a USask employee over the summer months, and we've been working on a project related to Higgs bundles and quantum matter. And so that's what he's going to tell us about today. And you can already see from his first slide, Elliot is not only a top-notch mathematician, but he's also an incredible artist. This is just a small taste of the fantastic imagery he's produced. And I'm sure he's going to treat us to more as the talk goes on. So I think without further ado, Elliot, please take it away and tell us about hyperbolic matter through Higgs bundles.
Thank you for the very kind introduction. And I think that covers, the title slide well enough. So just so you guys know roughly what we're going to go through. So here's what we're going to do. First, we're going to talk about, the first part of the title, which is hyperbolic band theory. What is it? Why do we care? That sort of thing. Then we're going to move on to the second part, which is Higgs bundles. And that just leaves the third part, which is the through. So we're going to connect the hyperbolic band theory and the Higgs bundles together into one and see how we can apply hyperbolic band theory and Higgs bundles together to create one overarching theory. It's the hope, at least. So to start, so my spies told me that this group is more of a Higgs bundle group than a quantum stuff group. So let's start with some maybe a little bit broad overview about the physics that's going on, which is condensed matter. So what even is condensed matter? Well, condensed matter is the study of cold things, cold from a physics standard, but like stuff where it's low enough temperature that you can have interesting interactions between particles that don't just fly past each other. Most of the time, this manifests as like electrons, like on a metal or a semiconductor. What we'll notice is that these aren't just electrons, sitting out in space generally. They're always on a medium, right? Like the metals and the semiconductors, both of these are crystals. This is what the electrons live on. So this is sort of where, the ballpark of condensed matter takes place. This is where a lot of it plays around, is on these crystals. So that means the sort of central question for condensed matter theory is, how does this crystalline background, how does the periodicity of the background impose on the how does it impose on the electron that's zooming around into space? So the answer to that comes from Bloch's theorem, which says that, it isn't the electron states, they're not quite periodic. They are quasi-periodic. So just to remind you, like an electron can be described by a wave function. That's just a complex valued function on the plane. And quasi-periodic means that as I move one period in the lattice directions, I'm just going to pick up a phase, right? This phase out here, K, right? So that's called the crystal momentum. And then once we split into these states, we can ask, okay, for all of the states with this given quasi-periodicity, what are the energies, okay? And then we can kind of plot those energies over the space of crystal momenta, and we get a band theory. So physicists have gotten, they've gotten very, very good at this over the last almost century since Bloch found his theorem. So, there's been peace and there's been harmony, and it does not last because of this. So, it certainly looks intimidating, but what is it? So this is it's a quantum electrodynamic circuit where basically each of these points has a state, and the states are interacting with each other, but the details don't really matter. What matters is what it's trying to approximate, which is this. It's a discrete model of essentially an electron on a hyperbolic plane. So when I say hyperbolic plane, what I mean is this plane with a constant negative curvature metric on top of it. And we're assuming that basically that the structure of this graph here is that of a tiling of the hyperbolic plane. So this tiling is described essentially by a lattice. You take some subgroup of, the symmetries of the plane, which are the isometries of this constant negative curvature metric, that lattice. And you can see as we plot a single point, as we go around the lattice, it goes all over the place. Now, I'm just going to comment that, this certainly doesn't look very regular the way I drew it, but I mean, that's just more of a consequence of the fact that, hyperbolic space really does not like embedding in R3 or even R2. So it's kind of hard to draw accurately. So what I'm doing is it's called a Poincaré disk model. And basically what you should imagine is that as I get closer and closer to the edge, these distances get larger and larger. So it all like balloons out, right? So that's sort of the picture that's going on. So why is this an issue? The issue is, like, they measure this and they see band theory, but it doesn't really work in the same way, because like the usual notion of band theory doesn't generalize to this situation very well at all. Sorry, it's difficult to generalize. So there's stuff to do, there's work to do. And that work to do is trying to develop a hyperbolic band theory. This is what Dr. Rayan has been doing for the past couple of years. So I'm going to kind of give a summary of the lay of the land of that to get us in the right frame of mind with Higgs bundles. Okay. So let's be a little bit more precise about the stuff that I was talking about. When I say an electron on the plane, what I really mean is, well, it's evolving under Schrodinger's equation, which means its time derivative is given by this operator, this Hamiltonian operator. And in this case, it's just going to be a kinetic plus potential. So it's the Laplacian plus some potential. And for it to be a crystal, to describe a crystal, we need this potential itself to be periodic, right? So like this lattice on here, the potential is periodic on this lattice. And then the question is, what is the spectrum of this guy? Now, to look at that, we need to pull back a bit and see how it interacts with the symmetries. So, what are the symmetries? Well, there's this translation operators that just take a function and move it along, a given vector of the lattice, right? And this forms a group. Okay, that's a typo, but if we look over here, if I compose two translations, you're going to get a third translation that's just, a translation of the length of those two added, right? And a consequence of that is that these translations are going to commute with each other. And that's exciting because you know what commuting operators do? They have a simultaneous eigenbasis. Basically, I can choose the set of states that, where their transformation rule, basically specifying their transformation rules. So I specify basically a representation row from, our lattice, which in this case is just, it's just an integer lattice. It's just z squared. And I map to U1, the set of phases. And for a given choice of that, what I'm going to consider, I can consider that the subspace of Hilbert space consisting of functions which transform according to that, which have this property that when I hop over one lattice cell, I pick up the specified phase. Right? You can kind of see that down here. As I move over one, it always just rotates a little bit, right? And this is called the crystal momentum. So the fact that these are symmetries means that not only do they commute with each other, they also commute with the Hamiltonian, which in particular means that the Hamiltonian respects all of these, essentially these eigenspaces. So the Hamiltonian sends this eigenspace we were talking about earlier, it sends it to itself, which means we can restrict the Hamiltonian to that space. And basically when we restrict to that space, we can look at its spectrum, which is just a bunch of points. And now we can vary, as we vary the choice of the crystal momentum over the allowed spaces of crystal momentum, that's how we get our band theory. So the allowed spaces of crystal momentum, well, these are homomorphisms from an integer lattice to U1. In this case, it's just basically a choice of, okay, if I go to the right, how much do I rotate? If I go up, how much do I rotate? It's just a torus, right? U1 cross U1. So for each point on this torus, I graph a bunch of sheets. I graph a bunch of energy levels. And as I move around a torus, these energy levels sweep out sheets. And this is called a band structure. Now, sometimes they might cross and then they kind of pinch together like this. That's not a big deal. So we can sort of look at a more geometric picture of what's going on, get a better sense. So it's sort of a dual notion of that we're considering. just before, we treated the crystal as its symmetry group, basically the symmetry group of the whole lattice. But now let's just zoom in on one little part, a unit cell. So if we look at a unit cell, so the shape of that gives us the whole information about the whole lattice, right? I can just take this cell and I can translate it over all of these different places. And that reproduces the lattice. So we just cut out a single unit cell. Now, there's extra information in this because we know that the things identified by lattice transformations have to be identified. So after we cut it out, we can start kind of trying to roll it up and fold it together. So we bend the yellow guys together and we bring the red guys together, and then we end up getting a torus, right? So the unit cell of this lattice is best described as a torus. Now with this picture, we can imagine a sort of different representation for the homomorphisms we're considering, because basically we're considering that the electron has to have its phase rotate by a certain amount as you jump from this edge to this edge. Well, let's consider just sort of plotting, if we kind of track the phase as it moves along the torus, as I sweep out this cycle, when I get back to the start, I'm gonna have a rotation. I'm gonna jump a little bit, right? I'm gonna have a specified monodromy of the phase. So that there's essentially this correspondence, these homomorphisms from Z2 to E1. Z2 is the fundamental group of a torus, right? So this corresponds to essentially flat line bundles on a torus, which like themselves, you can treat as holomorphic line bundles. So the space of holomorphic line bundles, that's a familiar object from algebraic geometry. It's called a Jacobian. You can see it up here, right? It's a dual because it's facing the other direction. This one's vertical, that one's horizontal. Okay, so this is like the momentum space, this is the position space. So that's the Euclidean case. Not too crazy. Now let's try the hyperbolic case. Because the real struggle is, most of that I said earlier is very general. It's about general symmetries, right? How symmetries work. But the trouble is, the symmetry group of the lattice, it's non-abelian. Right, let's consider this. If I hop up one direction, so move from this cell to this cell, and then like down right to the next, move to this cell. Let's try the other order. Down right, and then up. Oh, you can see they're really far from each other, right? So it's not abelian, which means that we don't have these nice simultaneous eigenspaces that we had before. But instead, we can think about it this way. We still have these translation operators corresponding to hopping, moving according to a given element of the lattice, right? And that specifies a unitary representation from the lattice group to, the whole Hilbert space. And we can split this representation into irreducible representations, just basically n-dimensional subspaces. And when we restrict to these, basically what we're considering is, some set of states, a bunch of functions, which when you apply these lattice translations, they just mix into each other, and that's it. Like they don't get anything else, right? So, if you want to be a physicist about it, you could call these a multuplet. So this actually gives us a really similar splitting to the one we had last time, because now we can split according to not just one-dimensional representations, but all irreducible representations, and basically say, a vector belongs to the subspace of a given irreducible representation if it belongs to some multuplet that transforms under that representation via the lattice translations. And once again, these are symmetries, which means the Hamiltonian respects these guys, which means the Hamiltonian preserves these subspaces. So you can do the same exact thing, and you can say, okay, let's just look at the spectrum restricted down to this space, right? So that's the band structure in this hyperbolic setting. It's about the spectrum of the Hamiltonian restricted to these guys, and you're looking at that spectrum over the space of the different irreducible representations. Okay, now let's go back to geometry. Right, we can do the same pictures before, but now with hyperbolic crystal, right? So see, I've kind of highlighted a unit cell, and I'm going to do the same thing. We're going to cut it out. And then we're going to identify the edges that are related by lattice translations. So we cut it out, and then we start kind of rolling it up. So these green guys go up here, and then these purple guys go here, red together, yellow together. And what you end up getting is, well, in this case, you get a genus 2 surface. Yeah, so this is actually a much more general thing, is that any discrete subgroup of the isometries of a hyperbolic plane, once you quotient out by that, which is effectively what I'm doing here, you will always get a Riemann surface. And moreover, every Riemann surface comes from this construction. So there's an exact equivalence between basically this unit cell, this Riemann surface picture, and this lattice picture, right? Okay, there it is. Now we can do, again, the same thing. But, you know, the argument that I gave about U1 bundles, the argument that I gave about, you know, phases, it still applies in the same way. You know, if I consider like the phase it rotates that certain amount, then that's equivalent to a line bundle, where if you do a monodromy that goes around this purple loop, then it's going to rotate that amount, right? So for rank 1 things, you do get back just, you know, the Jacobian. But for higher rank things, there's a similar story, although it's a lot harder to prove. And there's this theorem by, it's a lot harder to prove, but you do get vector bundles. And there's this theorem by Narasimhan and Shashardi that describes which vector bundles you get. Specifically, you get the stable bundles, where stability is just a condition on, it's a condition on the degree of the vector bundle and its relative subbundles. Right? Specifically, a degree 0 bundle. Okay? It's this space here. So this is our hyperbolic band sphere picture. Here are the momentum spaces. It's like this whole stack of disconnected spaces corresponding to the different, you know, to the different moduli of vector bundles, right? So for the n=1 case, we just get the familiar Jacobian. It's a nice torus. It's nice to work with. For n=2, you start to get this more complicated thing. n=3, it's even more complicated, and so on and so forth. So that's the momentum space. And on top of this, we have the band structure. So we have a bunch of these little sheeted covers over these, the moduli of the vector bundles. And in fact, we can describe what the Hamiltonian is really explicitly in this case. You know, we started with the Hamiltonian just being the normal Laplacian of the thing, which was d star d plus b. And the point is, when we restrict to, you know, the irreducible representations corresponding to a given vector bundle, what we're doing is we're changing our Hilbert space from the whole Hilbert space of L2 on the whole hyperbolic plane to just the Hilbert space of, you know, functions on E, where E is our vector bundle, L2 sections of our vector bundle. And when we restrict to this, the Hamiltonian actually reduces down to this guy right here, the twisted Dolbeault Laplacian, and then plus a potential. And it's worth to note that this is pretty much like the nicest operator you could have asked for, right? It's self-adjoint so that, you know, your band structure is going to be real. I mean, it better be if you want it to be physically relevant, right? It's an elliptic operator, and it's on a compact manifold. So that means that its spectrum is going to be, I mean, it's going to be nice. It's just going to be a bunch of points going up, and there's no accumulation points. And purely point-wise, everything just looks as like the pictures that I'm drawing pretty much. Okay, so this is the background of hyperbolic band theory, right? Now I'm going to try to introduce Higgs bundles. I'm going to do this through a motivating example. So let's suppose we have a crystal with spatial inversion symmetry. What do I mean by this? Well, basically, you know, you can have around any given point in hyperbolic space, you can have spatial inversion, which locally around that point, it just looks like multiplication by -1. And that's what, and, you know, since all of the points on the hyperbolic plane are the same, without loss of generality, let's just take this point to be, you know, the center of the Poincare disk. Makes life easy. In which case, the spatial inversion on the hyperbolic plane is exactly that you get from the spatial inversion on the disk itself, right? So, you know, our trick for the whole last section with the geometric structure of it was that we had an operator on the whole space, but instead we quotiented it out by the symmetry. So we have like the sort of the minimal unit cell, and then we described everything geometrically in terms of that. So we can do the same thing here. So, our space now is, this unit cell. But when we model by spatial inversion symmetry, okay, let's just take a single, generating set of that. So let's just take half of it. Why not? So what does the spatial inversion do to this guy? Well, it keeps each thing in the center, but basically it acts as a rule for gluing, tells you how to glue the edges together, right? So for example, this edge here, if this gets mapped over here, right, just multiplication by -1. So the net result of that is that it just folds this edge in half. Likewise, this edge right here, it jumps down to over here, but a lattice translation means that's just the same as this, right? So again, these all fold in half. And then this vertex is just kind of sitting there. And all of these points are the same point once you quotient out by the symmetry. So, so that's also a fixed point. Anyway, the net result is we get a copy of CP1, right? You can see here, I made this all ugly. Here's a picture of CP1 where I tried to emphasize the fact that when we fold these edges in half, we specifically get like cone points, right? Instead of the normal angle around a point is 360 degrees, around these, it's only half that, it's only 180. So you get pointy stuff. And then these yellow lines describe, these actual things that we folded to get this. So, from this point of view, we can see what our original Riemann surface looked like. It was just a double cover of this space, right? Because, we have one factor that's a CP1 and another factor that's a CP1, and, they merge together at each of these branch points, right? So, this whole exercise is just to say, spatial inversion symmetry are just like the lattices of spatial inversion symmetry correspond to hyperelliptic curves. And conversely, it's also true that every hyperelliptic curve can be drawn in such a way on the plane such that it has this nice spatial inversion symmetry, right? So then the symmetry, like it corresponds to just swapping the two branches of the cover. So it's like, it's the hyperelliptic involution is the mathy way to say it. So, okay, like the point was we wanted to describe things geometrically on the smallest minimal cell. And in this case, the smallest minimal cell was CP1 effectively. So how do we do that? Well, we start with our crystal data. Let's only deal with a rank 1 crystal for now, right? So it's on CP1 and, it's, the two branches of it. And what we're going to do is we're going to take this and we're going to squeeze it really, really hard, like a snowball, and kind of pack it all down. And when we do, these two lines that are distant, they're going to pop together into this single plane, right? This plane that is spanned by the two lines on each of the given, free images. So that's just it's a cute way to say what we're doing is we're taking the push forward of the line bundle, and we're getting in fact, a well and true rank 2 bundle on P1. So, ultimately, the idea with Higgs bundles is that we can encode all of the data of the crystal data, which corresponds to, a curve and a line bundle over the curve. We can correspond that to some sort of spectral data. Okay, because the curve itself is described as a cover over P1, and the cover, like, let's just look at over a single point, right? The cover is described by a pair of points, and let's just put those points in complex plane, right? And then the line bundle, those are described by one-dimensional subspaces. So, we can encode this by sort of having a matrix with eigenvalues giving, the heights of the two covers, and eigenvectors giving the corresponding lines. Now, a Higgs bundle is just a global holomorphic version of this construction, ultimately. Now, how does it globalize? Well, these subspaces turn into line bundles up top. This two-dimensional space turns into a vector bundle on the bottom. And these eigenvalues, well, they're locally in C. So globally, they're just in some line bundle. I don't know, let's call it N, why not? And then the the Higgs field, this guy whose spectral curve gives us, what we want, whose spectral data gives us the crystal data. This is a holomorphic section of, well, it's a matrix, so the endomorphisms of this base vector space, vector field, vector bundle. And then to get the eigenvalues in the right place, tensor with the line bundle. So, I mean, strictly speaking, what I'm describing is a twisted Higgs bundle, because usually we just take this to be the canonical bundle, but it doesn't really matter for us. Okay. How do we use this for actually doing stuff? Like, we want to look at the Hamiltonian, and we want to study the properties of this Hamiltonian of our crystal up top. And right, so we're looking at rank 1 momenta up top. So that's just the Hamiltonian. It's just described right here. So is there some operator we can put at the bottom where, like, basically the spectrum of this operator tells us exactly the spectrum that we want? Basically, we want a push forward operator, right? Because the push forward operation takes sections of the line bundle to sections of the corresponding vector bundle. And we just want to find the thing that makes this diagram commute. So there's a few things that we can do with this. Well, first off, practically by definition of the push forward of a line bundle, the push forward, this push forward of the Dolbeault operator for the line bundle is just that of the vector bundle. Similarly, this V, this potential, just a real function, the push forward of that becomes, once again, V times the identity on this base vector bundle, but that's only when we're looking at symmetric V, at spatially symmetric crystals. It's just a kind of annoying complication when it's not spatially symmetric. But let's just do this case, which leaves the real sticker, which is trying to take the push forward of the adjoint. Because remember, the adjoint, I'm not sure, so let's do this up here. So del star, that's star, del star, or maybe like plus or minus, I don't know. But the point is that these require the Hermitian metric. Sorry, these require the Riemannian metric on our Riemann surface. So this only pushes forward if the metrics agree. Namely, if the metric on the base curve lifts up to the metric we started with on the top curve. Oh no. So in the unramified case, if we have a situation where there's no ramification, it's just a nice Galois cover from top to bottom, well, then all of these are satisfied, and we're really happy because we just get down here, we end up just getting del E bar E plus B. That's just the Hamiltonian that we wanted in that's the Hamiltonian of a crystal. Sorry, let me try that again. This is the Hamiltonian for the crystal momentum on the base curve corresponding to a higher rank crystal momentum, right? A higher rank vector bundle. So basically, it literally gives us a correspondence between the band structure, parts of the band structure of the line bundle up top with that of the vector bundle on the bottom, right? It actually gives us a correspondence of two different crystals with each other. It's kind of cool. When there's ramification points, we're not so happy because, well, I mean, just look at the picture that I drew earlier, right? When we enforce this condition, basically what we're going to enforce is that, we have to fold up the thing, like I described earlier, which means we're going to get these cone points. And in particular, it forces that the metric on the base curve has to be singular. It's no good. So, I mean, I don't necessarily want to put this on the record because we're still working this out, but I think it's safe to say that how we deal with this is ultimately imposing this, trying to find the push forward operator in this ramified case. At every regular point, everything here is local, right? So it just works fine. Then we only have to deal with what happens literally at the branch points. And that's basically just you can think of that as imposing some boundary conditions, for a differential equation on the Riemann sphere, we impose that it takes the value 0 at these vantage points, something like that. So like the nice part of all of this was basically that, you know, with this pushing forward business going from, you know, the spectral curve down to the base curve, we actually do get things that are like the operators that these things correspond to are physically reasonable. These are like the operators we care about for crystals. So Higgs bundles gives us a way to basically trade complexity. If we start on a high genus crystal with low rank, we can trade that for a high rank momentum on a lower genus crystal. Maybe some singular points, I don't know. That's kind of cool. Okay. So what is this good for? Well, the interesting thing is that basically, let's move over to the full moduli of Higgs bundles. I forgot to include that slide. So I'm just hoping that people are relatively comfortable with this. We can look at the moduli space of all Higgs bundles, which is, you know, so there's this Hitchin base down here. And we consider the space above it, where the fibers of any given point on the Hitchin base, this point on the Hitchin base basically determines the spectral curve. And then the fiber of that is going to be a torus. Let's put it right there. It's going to be the torus. That's the Jacobian of, you know, the curve defined by this point on the base. Sometimes there's going to be singular parts of the base, like a discriminant locus. And especially at the very center, as Rayan asked her, it's the nilpotent cone. But you know, like for now, we can just sort of look at the regular parts and not worry about that. But yeah, so the point is we have this whole moduli of Higgs bundles. And this moduli of Higgs bundles, it glues together, you know, the relevant, essentially, momentum space for rank one momenta, rank one crystal momenta for all sorts of different curves. So like as we like sweep out the curve at the bottom, we're sweeping out this whole like space of different, you know, it's basically, it contains all of the momentum spaces. And that means that we have the band structures on each individual momentum space. If we just put them all together, we get a band structure on the whole Higgs moduli space. Yeah, so this is it's kind of like a universal band structure, because it's like looking at band structures from more of a moduli space perspective. Like we have this big space where if we just restrict it to any given fiber, and that tells us exactly the band structure that we want for, you know, the stuff at that fiber. Like this universal statement is especially nice in the case of, say, genus 2 curves, right? Where every genus 2 curve is hyperelliptic. So the moduli of Higgs bundles that give, you know, genus 2 spectral curves over P1, those are just going to be, it's going to have every single genus 2 curve. So you can really get every curve from this construction. Where'd it go? Yeah. So then like these level crossings that we talked about earlier, like in this case, there was just a single point. Then these turn into whole submanifolds of the Higgs space. So basically this tells us, you know, what our band theory wants to look like in this Higgs bundle picture. It's not just a band theory over individual Jacobians or individual moduli vector bundles. It's like this Jacobian on the whole moduli of Higgs bundles. So that's one interpretation. But what interestingly, there's another way that Higgs bundles come up in a really natural manner. So if you think about it, the things that we just did with like spectral curves of Higgs fields, it's like tantalizingly close to looking at band structures, right? Because we're just like, basically we're graphing the eigenvalues of some operator as you move over a point on the base. And that sounds really similar to, you know, exactly what you do for band structures. And I think it was actually, if I'm not mistaken, this was the observation that first prompted Dr. Rayan to, you know, explore hyperbolic band theory.
Say we tolerate R, but perhaps not gladly.
We tolerate error, but not gladly. Okay, yeah, but the thing is, we're not going to tolerate error because we're actually going to switch to a regime where algebraic geometry is a little bit more happy. And that's what we're going to allow complex energies, allow complex eigenvalues, which essentially means we're not going to enforce that the Hamiltonian is Hermitian anymore. So to enforce the Hamiltonian was Hermitian, remember, we looked at homomorphisms of, from the lattice to UN. Well, let's just forget UN and let's do any GLN. So we can basically have it, now it can scale up and down as opposed to just rotating, right? And now, this guy, we talked about this was the moduli of stable bundles. But this bigger thing, this is pretty close to just this character variety is the moduli of Higgs bundles. So this is the other way that Higgs bundles come in as a sort of generalization to complex momenta. So to sort of get a sense of what's going on, a real momenta, something in this space, it looks like just a nice sine wave. But when we have imaginary momenta, these sine waves just become exponentials, right? And we can look at the space of possible momenta now, if we just considered real momenta, we just had U1, right? But now that we can have imaginary momenta, then we can go to positive infinity or negative infinity or any nonsense like that. And the reason why physicists don't like doing this is because, well, a non-Hermitian Hamiltonian, in particular, it means that it's not going to conserve particles, right? Like the motion of this sort of wave function over time, it's going to move to the right. And since it's an exponential, that's exactly the same as just kind of scaling down, right? So it's like our particles dissipating away into nothing. Which is concerning to say the least. But we're in math land, we're in AG land, so we accept physical, we accept it when physics isn't happy, right? So to actually see how this complex momenta comes into play and how it relates to Higgs bundles, basically we trade, remember our Hamiltonian, just rewrite it, our Hamiltonian was this guy, del bar E plus V, right? And we're going to, the equivalence between flat bundles and holomorphic bundles means that this Dolbeau operator, that's just the flat connection for some choice of connection. I put an I here for this next part because when we include a Higgs field, right, which is a pair of a holomorphic structure on our vector bundle and a Higgs field, and we also get a canonical flat connection. This is the non-abelian Hodge correspondence. But in this case, what we get this by adding this sort of basically the real part of the Higgs field, or just the Higgs field plus its Hermitian conjugate. So something to make this a Hermitian operator. But when we add that, because it doesn't have an I, when we put it inside, now look what our momentum is. It's the real part here, but now there's also this extra imaginary part, right? So that's why the Higgs fields literally, they parameterize the complex momenta. And, if you look at it in terms of the character variety, then it's adding the Higgs field that tells you how much it decays over time, like the non-UN part, GLN. So let's look at the band structure for this now. Because now we have essentially from those flat connections I just described, which look like this, now we have totally different, now we have a different Hamiltonian. So we can look at the band structure for it. And now, this band structure is nice for AG people because it's complex valued. So that's the big difference from the last one. Well, you know what? Let's actually compare them directly, right? So here's the last one over here. Here's the new one. And so the last one we described was specifically by lifting to the spectral curve, considering that as a crystal and looking at that Hamiltonian. That's kind of a crystal moduli interpretation. It means that the Higgs moduli space is like a moduli space of different crystals and their crystal data. Conversely, what I just described is like a complex momenta interpretation, where the Higgs moduli space, is the space of the complexifications of the momentum. And these two operators, they give different band structures. This one is self-adjoint, it always gives real values. This one is, it's not self-adjoint. So you get complex values and stuff like that. Now, in particular, just to, just to not leave you hanging too much, the band structures, what is this? What are some actual differences? Well, for example, because it's complex, it means that the code emission where they cross is just going to be lower. I mean, it's going to be the same in complex dimensions, but in real dimensions, it's going to be twice as big, right? So instead of having a nice line of these branchings, these crossings of the spectrum, it's just going to happen at points in this case. I do also want to notice that I was careful over here to make these get all big as you go apart. Well, in here they kind of don't. They stay at the same amplitude. So the reason for that is, if you remember back here, that was a mistake. Let's go back. Sorry. Yeah, like here. See, the real part is constrained, but the imaginary part, that can go up real big, right? So this is the Hitchin base is sitting down here. And as we asymptotically go in a given ray on the Hitchin base, that's kind of a way of scaling the Higgs field to infinity. So in this real case, as that doesn't really much change the spectral curve, or at least in the specific example that I'm drawing here, it doesn't change the spectral curve. My laptop's about to die. I'll be right back. Yeah, so so it doesn't really change the spectral curve. So the Hamiltonian doesn't change much. Conversely, the complex thing, that means that this thing is going to get really, really big. And it's kind of like the momentum gets really large. And, it's kind of like a semi-classical approximation. So that's what this is kind of trying to represent here. So there's differences between these two pictures. The relationship, though, it's still kind of mysterious to us right now. Okay, so take a breath. This is ultimately how Higgs fields play into band theory. At least the picture that we have so far is that the Higgs fields, they naturally arise in a couple different interpretations, either as giving a moduli space of different crystals, or as giving a natural complexification of the momentum space. And these give rise to two different Hamiltonians which have their own branching structure. Now, that's the what. Now comes the, who cares though, right? What does this actually let us do? Because so far, everything I've described, it's just taking stuff you already know, the band structures over, I don't know, like a Euclidean torus or something, and just kind of sticking them all together willy-nilly in a big moduli space. So now look, it's all coming from the same moduli space, but we had to know everything already to put it in there. So it's not obvious what insight this tells us. But instead, here's how I think these Higgs fields will become useful. I think they're going to be useful because they facilitate interconnections between different fields, right? Higgs bundles are they're like an ambassador, kind of. They relate to all of these different fields of math and physics, I don't know, high energy physics and integrable systems and conformal field theory. It relates to all of them. And then through the bridge of Higgs bundles, you get these relationships between the fields that are sometimes really, really fruitful. So now that we had sort of a correspondence from hyperbolic matter down here to Higgs bundles, we can sort of back propagate this through this whole web that is built up over the years and see, what does this say about hyperbolic matter? So this is perhaps irresponsible of me, but we're all friends here, so why not? Let's fantasize a little bit and try to imagine what this story might look like, how everything might fit together, some baseless speculation. Okay. So I apologize in advance. I'm going to be saying a lot of big words soon without explaining them in the talk, but hopefully some people, you'll be able to latch on to something. Okay, so the first thing, High energy physics. Basically, Higgs bundles are no stranger to physics, but it's usually on the other, I guess, the other end of the pond, right? Where there's it's not cold, it's hot, it's high energy physics, right? So the place where they usually come up is in supersymmetric field theories. For example, n equal 2, d equals 4, right? So this is through the lens of Seiberg-Witten theory that relates these Higgs bundles, like each Higgs bundle becomes a theory. So, going through this thread, we can sort of take a crystal and get a field theory, to have a sort of dictionary between these two. That's kind of cool. But the real interesting thing about this isn't necessarily the physics. What I want to focus on is sort of mathematical implications, because the reason why people have been caring about these high energy physics relationships for Higgs bundles recently is, at least I think it's because of the work of Gaito, Moore, and Knightsky, where they developed conjectures on the asymptotics of the hyperkähler metric on the Higgs moduli space, coming from this physical motivation of field theory. So, some of the stuff they used to do that, like they used an exact WKB approximation, which is sort of like, it's a sort of semi-classical approximation. Now, in the asymptotics of the Higgs moduli space, that's the limit where the Higgs fields go to infinity. And remember, I just talked about that for the complex momentum interpretation, because when the Higgs fields go to infinity, it's like the complex momentum is getting really, really, really large, which means it's also kind of like a semi-classical approximation, right? So there's kind of like a similarity there. And it goes deeper, because when you start trying to work with this, like these asymptotically large imaginary momenta, you find that essentially imaginary stuff is dissipative. And it just, since like we're taking the imaginary part to be huge, anything that opposes the imaginary thing, anything that's non-zero, is just going to die immediately. So you're basically going to be constrained to lying on the cases where, it doesn't bother the imaginary part, right? And in the specific example of looking at, hyperelliptic curves over P1, these are essentially it's saying that the dynamics are constrained to the trajectories of the quadratic differential, right? So like here's a quadratic differential, this is a 0, maybe some poles over here, and there's trajectories that go like that. And basically the dynamics are going to make it lie along these trajectories. It has to. And then on top of that, so this is extremely similar to the stuff that happens in the Gaito, Moore, Knightsky paper for how they actually build like this conjecture and talk about they use this, what they call a WKB triangulation from a very similar structure, right? And moreover, there's also a component in this limit as the Higgs field goes to infinity. There's like this potential component, which gets really, really strong around the poles, and it's just like this infinite potential well. So as the Higgs field goes to infinity, basically your eigenstates are all going to concentrate around these guys. Oops. Your eigenstates are all going to concentrate around those guys, and what you get is like in that limit, it's like a tight binding limit from condensed matter. You get something that's eerily similar to the description of BPS states using quivers. So there might be a lot there. I'm hoping to maybe work on that more over the school year, but that's just one aspect, because there's lots more to math than just n equal 2, d equal 4 supersymmetry. Where is it? Yeah, large complex momentum. Okay. Okay, so another thing, what about brains, right? So something we care about a lot in physics of these hyperbolic matter things is symmetry, right? And specifically high symmetry points of these momentum spaces are hugely important for understanding the behaviors of materials with a given band structure. So, I mean, these high symmetry points, they come from sort of involutions on the base lattice, or I guess the base curve, you could call it. And all of this stuff, like this corresponds to operations on the Hitchin moduli space. And these high momentum points are like fixed points. Basically, the fixed points in I can't zoom in. The fixed points in the Higgs and moduli space are like the tracing out of the fixed points of these guys. So for example, in this picture here, you can see the sort of stuff I sketched here, these little these little things, like these are what happens when you sketch out like the high symmetry, the two torsion points on any given fiber in this case. And it traces out branes, right? Now this brane actually, this again connects to the Dieter-Mornitsky stuff, because this actually gives us a correspondence between the hyperkähler structure and the band field somehow. Because a lot of these branes that you end up getting are, for example, I don't know, maybe they're type ABB, meaning that they're Lagrangian in one Kähler structure and coherent sheaves in the other two, right? But that's a condition on how the brane structure relates to the metric, right? So this could actually give us a bridge between actually, you know, dealing with band structures of hyperbolic materials, like a window into how this relates to the asymptotics of the hyperkähler manifold. Okay, now let's go all the way over here. Let's talk about the geometric Langlands now. That's exciting. So this again acts on the Higgs and moduli space. This time it acts on T-duality, which means that, you know, this is a fibration by abelian varieties. So for each fiber, what we do is we send it to its dual. We send this upright one to its horizontal one and back and forth, right? And this is sort of the way that geometric Langlands program manifests in a lot of ways. It comes from this duality on the Hitchin system. And again, well, that's interesting because, you know, this T-duality is sending a variety to its dual. That sounds a lot like sending position space to momentum space, right? I mean, that's exactly what it is. So, you know, this is something that comes up in hyperbolic matter, you know, in a reasonably natural way. And, you know, this operation that you do, it somehow corresponds to geometric Langlands. But wait a minute, because geometric Langlands corresponds to all of this stuff. Because this geometric Langlands, this T-duality here, it manifests as a sort of S-duality on these four-dimensional theories, right? So, you know, this web is starting to get really tangled now, right? And also, you know, one of the ways you define geometric Langlands, you know, in the Kapustin-Witten approach, it's a duality on branes in particular. So again, you have this relationship here between Langlands and branes, okay? Okay, and now another spot. Okay, let's do a more physically related one. Let's talk about the fractional quantum Hall effect. So this is sort of the logical next step if you just care about physics for what to do, because this is where all the interesting physics nowadays is happening. Basically, this is what you get when you start turning on interactions between particles. And then you get like really high magnetic fields. And then all of these horribly complicated stuff happens. And like it's this whole industry, right? So there's an actual physics path pipeline, you know, from going from what we're considering, which is the band theory of a single particle, to interacting particles and fractional quantum Hall effect. But these also come from Higgs bundles. Because the fractional quantum Hall effect has a conformal field theory description. And like the states that we care about in these guys, which are called the Laughlin wave functions, these are just the conformal blocks, and these conformal blocks in turn are sections of the beta line bundle on this Higgs moduli space, right? So again, two different ways to get to the same thing. And again, geometric Langlands also acts on the fractional quantum Hall effect by duality, right? So you can kind of see what's going on here. Like sitting at the Higgs bundle, it has this tangled web of all of these different areas of physics. I just drew a few of them. There's way more that I could have put in, right? You know, this little spider, it has legs. And hyperbolic matter, you know, through Higgs bundles, it can map to all of these things. But interestingly, the way that it maps, like the actual operations that you do, almost always have physical interpretations in terms of hyperbolic matter. So like you can map through this web of relationships in a lot of different ways, and it's really not obvious what the relationship between these different paths are, right? So let's take as an example the fractional quantum Hall stuff, right? There's two paths there, right? Starting from hyperbolic matter, there's the physics pipeline with interacting states. And alternatively, we can take our hyperbolic matter and then pass to a sort of Hitch and moduli space, and then look at the beta functions on that. And those also give us fractional quantum Hall states. So like, are these the same? It'd be cool if they were, wouldn't it? I don't know. It's basically like, I don't know, maybe I'm just, young and naive, but it really feels to me like we're kind of glimpsing like just like little glimpses of this wider beast, this beautiful machinations that are going on behind the scenes, just catching glimpses through the fog of, this really deep story. And, there's all of these different paths you can take from this. There's all of these different relationships. And it would just be so cool if they were somehow all the same. It doesn't matter what path you take to get from basically hyperbolic matter. I can send it off into the wide world of mathematics through the web of Higgs bundles in any way I like. And no matter how it comes back, if it was somehow equivalent, that'd be cool. I can't call this a conjecture because basically the only evidence is aesthetic, but I can call it what it is, which is a daydream. The daydream is that this diagram commutes. Okay, and that's all I have to say. Thank you.
Okay, thanks so much, Elliot. Let's all give him a round of applause. So it's quite an inspiring talk and very beautiful, not only in the concepts, but obviously, of course, in the various artistry, visual artistry occurring throughout that talk. Do we have questions for Elliot?
I just have to say that it's the best presentation I have seen since a while. So great job, really.
Thank you.
Very, very great.
Oh, thanks, Ahmed. I'm glad that your first talk since joining us has ticked all the artistic boxes you were looking for.
Yeah.
That's great. Well, it's not a question, but I just, I just want to say that, there's a lot of potential for commutativity within this particular diagram that you've set up here. And, I think there's a few years of work here to come to understand all of this in detail. But, I think that there are a lot of plausible connections here that will be important for both communities, the math and the physics community. And even in the physics community, I'm referring to both, obviously condensed matter, but also high energy.
So you said earlier that you weren't really interested in restricting to only Higgs bundles that are twisted by the canonical line bundle.
Mm-hmm.
But I feel like the way Higgs bundles interact with most of these other areas on your diagram, they really are those, classical Higgs bundles.
Yeah. So the real situation is I didn't really want to complicate stuff by introducing parabolic bundles, but that's, I think, the ultimate way to do it, is that you can take these twisted Higgs bundles as just meromorphic normal Higgs bundles, right? By introducing a divisor and twisting the canonical bundle by that divisor. So I guess that's the more proper way to do it, is with parabolic bundles, but I didn't want to get into that in this talk.
Just for the case of when you're over P1, at least, is that what you're saying?
I think it'd be parabolic in general. Like twisted Higgs bundles and parabolic Higgs bundles, in my understanding, are kind of dual pictures.
Okay. But in most of these other worlds that aren't, the Higgs bundle world in the middle,
mm-hmm.
They all deal, in my understanding, with, Higgs bundles that are twisted by the canonical.
Yeah, so the parabolic bundle, you can think of that as a Higgs bundle on a punctured surface, just a normal Higgs bundle on a punctured surface, and then you prescribe some sort of singularity structure as you go towards those punctures. So they might not say parabolic bundle in a lot of these things, but it really comes up all the time in my experience.
I definitely think that's a reasonable answer to Evan's question. In some sense, you can pass from twisted Higgs bundles to parabolic Higgs bundles. You have to make a choice of parabolic weights. Those aren't a given in the twisted picture, but you can make some judicious choices. But I guess as an extension to Evan's quite natural question, one can go beyond parabolic bundles and think about irregular Higgs bundles. You know, we could think about Higgs bundles with poles of very high order, for instance. Even the case of, say, P1 with a single pole at infinity, but of arbitrarily high order. And are you perceiving yet a role for these in the work we're doing?
So at the limit of my experience of non-parabolic Higgs bundles, like the wilder ones, comes in this area where, like, even in the simplest Seeberg-Witten theory of just SU2 gauge theory, like you have these, these order 2 poles instead of order 1. And it always just really confused me because I didn't know how to deal with that. Basically, the answer is I don't know enough to really say.
No, and that's fine. And it is something we'll think about in the near future, I would say. Any other questions for Elliot?
I have a question for Elliot, if that's okay.
Yeah, Sheldon, go ahead.
Yeah, great presentation. Yeah, the drawing was amazing. It was I always said you probably got definitely a career as an artist if you decide to for some reason decide not to pursue mathematics. But I guess my question was, maybe, and this is something I just missed. So in the Euclidean case, you talked about the associated lattice as being Z cross Z, and then you talked about that as the fundamental group of the torus. But when we move to the hyperbolic case, I'm assuming the lattice structure has changed, right? Because we're no longer dealing with a torus, we're dealing with other structures. Yeah, or is the lattice still Z cross Z, or is it? Because I noticed you referenced it as L throughout.
I probably should have specified this more carefully, but no, it's absolutely not the same group. The lattice that you get it's called a Fuchsian group. Those are the ones that we're talking about, and they are ones that are isomorphic to. Ultimately, they're ones that are isomorphic to the fundamental group of a higher genus muon surface.
Right. Okay. Yeah.
They're just both gamma because I got too lazy to come up with a new symbol.
Oh no, that's great. Yeah, that clears it up. Yeah, I thought sort of the pattern remained the same of them being associated with these fundamental groups, but no, that's great.
Yeah, beautiful. Any other questions for Elliot? If not, I'll say that in the very near future, you can expect preprint on this subject, and you'll be able to pore over the details at that time. But until then, let's thank Elliot again for a brilliant talk. Great, and I'll stop the recording.